Assalamualaikum warahmatullahi wabarakatuh. Kami dari kelompok 1 akan mempresentasikan hasil dari PPT kelompok kami, yaitu tentang Rayleigh and Chain. Rayleigh dan Chain mengusulkan suatu model sederhana untuk menerangkan bentuk spektrum radiasi benda hitam. Penelitian mereka yaitu molekul atau muatan dini permukaan benda berongga dihubungkan oleh semacam pegas. Teori elektromagnetik dan termodinamika klasik menyatakan bahwa hubungan intensitas radiasi dengan panjang gelombang yang dipancarkan memiliki hasil yang dapat dibandingkan dengan kurva hasil eksperimen. Salah satu hasil perumusan klasiknya dikenal dengan persamaan Rayleigh and Chain. Di sini ada dua kurva, yaitu yang pertama kurva radiasi benda hitam Rayleigh and Chain dan yang kedua kurva radiasi benda hitam yang seharusnya. Pada kurva radiasi benda hitam Rayleigh and Chain, ketika temperatur berkurang, puncak dari kurva radiasi benda hitam bergerak ke intensitas yang lebih rendah dan panjang gelombang yang lebih panjang. Grafik radiasi benda hitam ini dibandingkan dengan model klasik dari Rayleigh and Chain. Kemudian, yang kedua, kurva benda hitam yang seharusnya. Seiring temperatur turun, puncak kurva radiasi benda hitam akan turun juga intensitasnya dengan panjang gelombang naik. Grafik radiasi benda hitam juga dibandingkan dengan model klasik Rayleigh and Chain.
Pertama, gelombang berdiri dengan simpul di permukaan metalik. Kedua, gelombang berdiri dapat dihitung dengan argumen geometri. Dan yang ketiga, energi total rata-rata hanya bergantung pada suhu. Maka terdapat variabel X, lambda, dan N. X menyatakan jarak ujung dikurang pangkal gelombang, lambda menyatakan panjang gelombang, dan N menyatakan banyaknya puncak, bukit, dan lembah. Untuk setiap waktu dinyatakan dengan T, simpul atau ujung berlaku 2pi per pi sama dengan npi. Dengan N dinyatakan dengan bilangan bulat. Ketika X sama dengan 0, maka 2πx per lambda sama dengan 2pi dikali 0 dibagi lambda sama dengan 0. Ketika X sama dengan A, maka 2πx per lambda sama dengan np sama dengan 2pi dikali A per lambda sama dengan np sama dengan 2A per lambda, maka dinyatakan dengan lambda sama dengan 2A per N. Panjang gelombang berbanding terbalik dengan frekuensi, maka lambda sama dengan 1 per V. Atau dalam kecepatan cahaya, maka dapat dinyatakan dengan lambda sama dengan C per V, sehingga V dinyatakan dengan NC per 2A. Dalam perubahan V sama dengan V ditambah Devi, yang memungkinkan yaitu banyaknya perubahan V terhadap Devi dilambangkan dengan N V Devi.
Jika U sama dengan NC per 2A kurang dari sama dengan lebih dari N sama dengan 2A per C dalam kurung U, sehingga perubahan N terhadap DN dengan DN sama dengan dalam kurung 2A per C dNu. NU dNu sama dengan 2 kali DN karena berlaku pada satu gelombang, satu bukit, dan satu lembah. N dalam kurung U dNu sama dengan 2 kali 2A per C dNu. NU dNu sama dengan 4A per C dNu. Dimensi koordinat X-Y, gelombang berbentuk setengah lingkaran dalam bentuk 3 dimensi, maka gelombang berbentuk bulat, sehingga luas permukaan permukaannya adalah 4πr kuadrat, sehingga N dapat diganti dengan R. R sama dengan dalam kurung 2A per C dikali U, sehingga R sama dengan 2A per C dikali U. Jadi, luas permukaan bola dapat dihitung dengan 4πr kuadrat dikali dr, sama dengan 4π dalam kurung 2A per C dikali U dalam kurung pangkat 2 dikali 2A per C dikali dnu, sama dengan 4π dalam kurung 2A per C pangkat 3 dikali nu pangkat 2 dikali dnu, sehingga nu dikali dnu sama dengan 2 kali 1/8 kali 4πr kuadrat dikali dr, sama dengan 1/4 kali 4π dalam kurung 2A per C pangkat 3 dikali nu pangkat 2 dikali dnu, sama dengan 8π A pangkat 3 per C pangkat 3 dikali nu pangkat 2 dikali dnu dengan A pangkat 3 sama dengan V, sehingga 8π per C pangkat 3 dikali V dikali nu pangkat 2 dikali dnu.
Gelombang berbentuk bola, maka luas permukaannya dapat kita hitung dengan rumus 4πr kuadrat. Nah, dalam 2 dimensi, titik koordinat x gelombang berbentuk setengah lingkaran dalam 3 dimensi. Nah, jadi di sini gelombang berbentuk bola, maka luas permukaannya dapat kita hitung dengan rumus 4πr kuadrat. Nah, sehingga R di sini dapat kita ganti dengan N, dapat kita ganti dengan R. Maka R sama dengan 2A per C dikali V, sehingga R sama dengan 2A per C dikali dV. Jadi, luas permukaan bola dapat kita hitung dengan 4πr kuadrat dr sama dengan 4π dikali buka kurung 2A per C tutup kurung V tutup kurung kuadrat dikali buka kurung 2A per C tutup kurung dV, sama dengan 4π dikali 2A per C kubik dikali V kuadrat dikali dV, sehingga NVdV sama dengan 2 dikali 1/8 dikali 4πr kuadrat dikali dr, sama dengan 1/4 kali 4π dikali 2A per C pangkat 3 dikali V kuadrat sama dengan dV. Nah, hasilnya 8π A pangkat 3 per C pangkat 3 dikali V kuadrat dikali dV, dengan A pangkat 3 di sini adalah bisa diganti dengan volume. Nah, sehingga 8π per C pangkat 3 volume dikali V kuadrat dV, jadi jumlah getaran dalam satu satuan volume yaitu N dikali V dikali dV per volume, sehingga NVdV per volume sama dengan 8π per C kubik dikali V kuadrat. Nah, berdasarkan ketentuan Boltzmann, energi total rata-rata adalah konstanta dikali suhu. Maka epsilon sama dengan N dikali konstanta kali suhu per 2.
Selanjutnya adalah pembuktian. Untuk membuktikan bahwa pada teori Rayleigh engines ini tidak dapat digunakan pada panjang gelombang pendek, dapat kita lihat dengan memasukkan nilai panjang gelombang pada persamaan intensitas berikut ini. Panjang gelombang merah sama dengan 700 nanometer atau 7 dikali 10 pangkat min 7 meter. Dimasukkan ke dalam rumus I atau intensitas dikali X sama dengan C dikali 2 dikali Pi dikali K dikali T dibagi dengan X pangkat 4, di mana C dan K adalah konstanta sementara T adalah suhu. Maka diperoleh 3 dikali 10 pangkat 8 dikali 2 dikali 3,14 dikali 1,38 kali 10 pangkat min 23 dikali 6000 dibagi dengan 7 kali 10 pangkat min 7 pangkat 4. Maka dihasilkan 1,56 kali 10 pangkat min 12 dibagi dengan 2,4 kali 10 pangkat min 28, maka dihasilkan intensitas sebesar 65 dikali 10 pangkat 16 I sama dengan 65 kali 10 pangkat 16, sedangkan pada panjang gelombang UV 10 pangkat min 9 menghasilkan intensitas sebesar I atau intensitas dikali lambda atau panjang gelombang sama dengan 3 kali 10 pangkat 8 dikali 2 dikali 3,14 dikali 1,38 kali 10 pangkat min 23 kali 6000 dibagi dengan 10 pangkat min 9 pangkat 4 sama dengan 1,49 kali 10 pangkat 26. Dari persamaan ini terlihat bahwa pada sinar UV, intensitas menjadi lebih besar, yang artinya semakin tinggi pada grafiknya, ini tidak sesuai dengan percobaan yang seharusnya. Pada panjang gelombang UV, grafik intensitas menurun. Sekian presentasi dari kelompok 1. Jika ada salah kami mohon maaf. Wassalamualaikum warahmatullahi wabarakatuh.
So what you can see here is a representation of a black body curve. Now before we study the actual graph here, we need to quickly review what a black body is. Now a black body is simply an object that absorbs all the radiation that falls on it and re-emits it in the form of electromagnetic radiation. So in sense of stars are generating energy by the way of fusion within their core. So the light you see from stars is totally due to emission. There's no reflection going on. So if you look at the black body curve, you will see that it has a very characteristic shape. Now the black body curve actually represents basically the intensity per wavelength. So in this particular image here, we're going to be looking at the sun. You see a distribution of wavelengths and with different intensities. So on the y-axis we have our spectral power density. So really it's just talking about the intensity for every given wavelength. And on the x-axis you see the wavelength. So the star that we call our sun in this case is giving a very characteristic curve or a black body curve. Now let's explore the parts of this graph here. So we're going to add our labels here and you will see that what we have here is the visible spectrum. We have our infrared range, and obviously the further we go away, the longer the wavelength. And at the other end you see the ultraviolet section. Now you'll see that there is quite a significant drop off in the ultraviolet section. Now that's not saying that the sun is not giving off any ultraviolet radiation, it is, but in terms of higher frequencies, the amount of radiation or the intensity of those ultraviolet significantly drops off. Now, the reason behind that I'm not discussing in this video, but I have a video, if you look on black bodies and Max Planck, and I'll put the link in the description below, then you can explore that. So looking at our sun, we'll see that we have a lot of infrared radiation, but we certainly have a lot more radiation in the visible spectrum. If you then look at that visible spectrum, although that we have here a differing amounts between our ultraviolet and our red, there is not a huge difference in terms of the intensities of these wavelengths. So what we end up seeing, as you can see here, this diagram up the top here, is the fact that we're going to see white light because we're getting equal amounts, roughly speaking, of the wavelengths that are in the visible spectrum. But now let's have a look what happens at the spectrum as I change the temperature. So I'm going to first lower the temperature and you'll see what happens is we're going to get a drop of intensity along all wavelengths. But if you look very carefully, you'll find that the peak actually drops. So let me take a photo of roughly where the sun is, which is this line, and then I'm going to drop to the radiation emitted by a light bulb like so, and I press a photo here and you can see that there is now a significant difference. So we have a drop in intensity for each of the wavelengths, but we also have a shift towards the right. In other words, the intensity of the wavelength that is of the greatest intensity is certainly moved towards the longer end. Now, the issue now here, of course, is the scale. So if I just reduce our scale of the y-axis, then we're going to get a better representation here. You can now see that the sun's graph is off the scale here, and here we have infrared radiation being the predominant form of energy. And if you know anything about light bulbs, at least your old style incandescent light bulbs, they're about 95% inefficient. That is, of 100% of all the energy they emit, the majority is in the infrared range. That's because the light bulb is acting like a black body and it's giving off, yes, light, but much more in terms of the infrared. Now let's again change our scale, and we're going to zoom out a bit, and we're going to increase the temperature as we go up. And I'm going to take a few snapshots of various energies as we go up. So here's a snapshot again, and I'm going to move my graph again, and another snapshot over here. And if you look very carefully, you'll find that our peaks went from here, now to here, and now to here. So in other words, as we get hotter and hotter, the wavelength with the greatest intensity moves to wavelengths that are shorter. If I turn this intensity on, you'll see I now have the area underneath the graph. So since the scale tells us the intensity per given wavelength, the total area under the graph is the total intensity of the light given off by the star. Now, what is intensity? It's the amount of power per unit area. So in other words, the sun gives off a constant, certain roughly constant value of energy, so therefore energy over time is power. But as we go further and further and further away, that power, that energy is spread over a much larger surface area. So the intensity, which is the amount of power per given area, certainly changes. So again, I would look at my video where I look at the relationship of the inverse square law in terms of intensity and distance, and there you can see where I talk about intensity in that regard. Now, what happens if we now get a hotter star? So again, I'm going to have to change my scales here. So now I have changed my scales, and I'm now going to a star that is significantly hotter. So we're going to jump way up to closer and closer, and I'm going to stop here because we're going to go about the graph here. In this case, we have a star that has a temperature of around, surface temperature at least, of around 8,250 Kelvin. You see again that the total intensity certainly is greater. So a hot blue star is significantly brighter. It has a greater intensity than, let's say, warmer, let's say, cooler stars such as our sun, and even cooler stars such as red dwarfs and so forth. But you again can see that the peak has moved more and more towards the left. So if I now turn on our graph values, you can see here the value of our wavelength and our intensity are given. So as I drop the temperatures, you'll see that as I move across, that both scales change. That is, the peak intensity shifts. And so as I move that across like so, you will see that that almost looks like an inverse relationship. And it is an inverse relationship. And we'll discuss that in a second. Now, here we have, of course, the representation of our star that is significantly hotter. We now have a lot of energy in the short wavelengths of our visible and, of course, ultraviolet. And so as a result, we see more blues and less reds and greens. And so we therefore have our blue star. If I go to the other extreme, where we go to the red dwarf, which is a temperature of maybe around 3000 Kelvin, like so, my scale is way out, so I'm going to change that scale so that we can get a better perspective. And there it is. You can see we have lots of infrared radiation. We have a lot of, in terms of the visible, the red end of the spectrum, but very little in the blue end of the spectrum. And so the star appears a reddish color. And so we refer to often this as a red dwarf. And the intensity, the total intensity, of course, is significantly lower than the sun, and even more significantly lower than the hot blue stars such as Sirius. All right, so now let's again scale back, and now let's have a look a little bit at mathematics, which is probably one of the reasons why you're watching this video. You understand black body curves, but you're also piqued by the term of Wien's law. And now, what is Wien's law? Now let's remind ourselves, who's Wien? His name is Wilhelm Wien, a German scientist in the 19th century, and he was the first to really establish the relationship between the wavelength that is of the greatest intensity with the temperature, and that's the key. So again, we're going to actually have our values showing here, and I'm going to get my temperature increasing. So as my temperatures increase, you will notice that the wavelengths are decreasing of that particular peak intensity. And therefore, what we have here is an inverse relationship between the wavelength that is its peak value with the temperature. So in other words, why this is useful is that if you can work out the maximum wavelength intensity, in other words, this particular value right here, then you can use this relationship, which we refer to as Wien's law, to determine the temperature of the star. So let's have a look at this. So it's an inverse relationship. So we know that the temperature is proportional to 1 over the wavelength, or we can write it this way, that the wavelength is proportional to 1 over the temperature. So that's the inverse relationship. So what we will get if we were to graph the wavelength with the temperature, well, you would get an inverse relationship like so. But if we now graph the wavelength with 1 over the temperature, because there's an inverse relationship, we get a straight line. And that tells us that the slope, that is the wavelength divided by 1 over t, is a constant value. I'm going to call that constant value b at this point. Now that means if I rearrange that, I get the wavelength is equal to b over t. And there is Wien's law. Now b ends up being equal to approximately 2.98 by 10 to the power of -3. So that's Wien's law. Wien's law is the relationship between the wavelength that has the greatest intensity and the temperature in terms of Kelvin, and it's a simple inverse relationship where the constant has the value of 2.98 by 10 to the -3. Now sometimes Wien's law is called Wien's displacement law, so it's basically the same thing. So when you look it up and you see displacement law, that's the same thing. So there we have the terms of the black body, why the curve that is very characteristic, that's related to temperature, and as a result, the formula for Wien's law. In any case, my name is Paul from High School Physics Explained. Please like, share, and subscribe. Hit that bell so that you get my latest.